Chapter 10 notes fluids in motion. The continuity equation says that fluid speed is greater where the area is smaller. This is used for water flowing through a tube that has different diameters to it. On the left side we have a smaller area, so we have a faster speed. On the right side we have a larger area, so we have a slower speed. Now you're familiar with this. If you put your thumb over a garden hose, you're making the area smaller, so you make the speed come out faster. The flow rate is defined as the area multiplied by the speed, or the volume divided by the time. Volume per time is a flow rate, and this flow rate has to stay constant anywhere within the moving liquid. The units are cubic meters per second. Bernoulli's equation has three terms to it. The first term is atmospheric pressure. The second term is kinetic energy divided by the volume. And we know if we divide mass divided by volume, we get density. So that's where the rho comes from. So the second term is the potential energy divided by the volume. And the sum of these three terms has to stay constant within the moving fluid. Bernoulli's principle tells us that the pressure in a liquid decreases as the velocity increases. So on the left side we have a large area with a slower velocity and a larger pressure. On the right side we have a smaller area, so it's a faster velocity but a lower pressure. Bernoulli's principle explains how a perfume bottle works. You might remember from the Millikan experiment they called the perfume bottle an atomizer. And the way it works is we squeeze the bulb, making a fast stream of air. That fast stream of air makes a lower pressure inside the tube, and the low pressure is going to suck the liquid up to the top. Then that liquid gets hit with the fast air and it sprays out as a mist. Bernoulli's principle is also used to explain how an airplane wing works. The air moving over the top of the wing is moving faster than the air going under the wing. The faster moving air has a lower pressure, and down on the bottom we have a slower speed, so we have a higher pressure, and that creates a force going upwards. That force is pushing from high pressure towards a low pressure. The way we use it in problem solving, we have a very large container with an opening at the bottom, and we want to find the speed of the water coming out at the bottom. So we're going to apply Bernoulli's equation to the top of the container and the bottom of the container. So the A's on the left side are for the top, the B's on the right side are for the bottom. The first term, atmospheric pressure, is the same at top and bottom, so those are going to cancel out of our equation. The second term, the kinetic energy here, the speed is so slow at the top because that diameter is so large, the height isn't going to change very much during the time. So we're going to cancel that out as well. Usually in the problem they will tell you it's negligible or near zero. The remaining terms all have density in them. So if we divide the density out, the leftover letters then can be arranged for the speed. This speed formula may look familiar. This was the same equation we used for roller coasters. If we know the height of the first hill and the height of any other location on the roller coaster, we can find the speed at that point. However, you're not allowed to pull this equation out and use it. You have to show where it comes from by going through all the steps that I just showed you. End of notes.